Okay, so picking up where we left off here, we were talking about the idea that if we want to solve, let me scroll back up a little bit. If I wanted to solve this single matrix equation for the variable x, that's sort of the same idea here. But so before we look too far ahead here, let's just think about something. If these were real numbers, if I just had a times x equals b, and these were real numbers, right? So I'd think about, like, how do I get x by itself? What do I do algebraically to get x by itself? So what I hope you're all saying is I would divide by a, right? Because dividing by a is the inverse operation of multiplying by a. And so if you do inverse operations, they cancel, and you're just left with x equals b over a, right? But we don't have division when it comes to matrices, at least not in the same way. So could we think about how to do this if there was like no such thing as division? So if we had a times x equals b with real numbers, is there another way we could use multiplication only to accomplish the same thing as dividing by a? So the answer is yes, we could multiply by what we would call the reciprocal, but what we're really doing is multiplying by the multiplicative inverse. Okay, so the multiplicative inverse of a is 1 over a. And we saw this above in that big chart. So if we multiplied both sides of the equation by the multiplicative inverse of a, which is 1 over a, the same idea that these things are inverse operations of each other, and so they cancel. We're left with just x equals 1 over a times b. Okay, this is of course equivalent to b over a, but this is avoiding division. Okay, so life was pretty simple with real numbers. We have a very clear multiplicative inverse of something a. But let's look at how we do this with matrices. So hopefully you already read the top of page 318. And so if we were looking closely at what they did on page 318, we have this algebra here that's worked out. So we start with our original equation, ax equals b. And we want to solve for x. Vector x. That's supposed to be bold. That does not look bold. That looks like craziness. All right, I can't even keep it. It's bad. Let's try that again. So we'll just write x. Maybe I'll just highlight it twice. Okay. So how do I do that? So think like you did with real numbers. How do I undo matrix multiplication, right? So what is the multiplicative inverse? So we want to multiply by the multiplicative inverse of a. And keeping in mind, as they say here, matrix multiplication is not commutative. So the side in which I do it matters. So I have to multiply on the left side here because I need the a inverse and a to be next to each other so that they're going to cancel. Okay, so I'm multiplying on the left. So multiply by the multiplicative inverse of a on the left because a is currently on the left. So multiply both sides of this equation by this multiplicative inverse. This is kind of like how we multiply by 1 over a in the real numbers case. Now, over here, I didn't even talk about associativity, right? I just naturally said, okay, I know this was ax, but when I multiply by 1 over a, I sort of in my head regrouped it. So I think all of us would in our head regroup this. I probably wouldn't expect you guys to write all this step down. But of course, officially, we are regrouping, so we're using the associativity of matrix multiplication. And so a inverse times a, that's going to give us I, where I, recall, is our identity matrix of whatever size the original matrix A is. And so on the left, we're left with just x, and on the right, we're left with a inverse times b. Okay? And so we've solved this equation. X, this matrix equation, x is going to be equal to a inverse times b. Remember, x is our vector or column matrix xy. So if we could just find a inverse times b, we could easily solve for xy. So now we do have matrix calculators online, so that makes finding a inverse pretty quick. But let's just talk about how we would do this sort of the long way, just to recap, right? So x is equal to a inverse times b. So the question is, what is a inverse equal, right? Well, how did we find a inverse? So we started with our matrix A, and we wrote an augmented it with the, sorry, erase that, with the identity matrix 1, 0, 0, 1. And then we performed elementary row operations until this left side was the identity. So these will be the exact same row operations as what we just did above because we've already done this work that would translate this matrix into the identity. So I'm going to quickly go through that. So row 1 and row 2 we would swap. So we'd have 1, 5, 0, 1 and 2, negative 3, 1, 0. And then the next elementary operation I did was I took negative 2 times row 1 plus row 2, and I let that replace my row 2. So that gave me, so I'm going to keep the 1, 5, 0, 1, but now my bottom row, sorry, another mistake. Going too fast. Then this is going to be 0, negative 13. This should sound familiar from what we did above. And then this would be 1 and negative 2. Okay, so we had already sort of seen this half of the matrix. Okay, the next elementary row operation we did was we want to get that 13 out of there. So we multiplied negative 1/13 times row 2. And that kept row 1 the same. But it changed the second row into 0, 1, and now I'm going to be left with negative 1/13 and 2, positive 2/13, right? Because I'm multiplying by negative 1/13, so that goes back to positive. Okay, and so next I want to change this 5 into a 0, so I did negative 5 times row 2 plus row 1, and that replaced row 1. Again, I'm expecting to see this kind of work when I ask you explicitly for this work. Okay, so what happens is I get 1, 0, 0, 1. Okay, and the bottom row is staying exactly the same. So let's just finish this part up here. So if I take negative 5 times negative 1/13, and then I add it to row 1, so that's 0. So I'm going to get 5/13. And then if I take negative 5 times 2/13, so it's negative 10/13, plus 1, so let's actually write this right here. So we're taking negative 5 times 2/13 plus 1, but that's negative 10/13 plus 1 I can think of as 13/13. So when I add those things together, I'm going to get 3/13 here. Okay, so this tells me that A inverse is the matrix 5/13, 3/13, negative 1/13, and 2/13. And we could have used an online calculator to find this pretty quickly, but I'm reminding you that we do know how to do this the long way. Okay, so let's just reread the question we're supposed to be doing. So it does say to find A inverse, but then it says to find A inverse times B. Okay, so that's A inverse. Let's see if we can fit in over here. I'm going to change the color just to draw this out. So A inverse times B is going to be this matrix 5/13, 3/13, negative 1/13, 2/13. So that's A inverse. And then B was the column matrix for 2. So again, I have a 2 by 2 matrix multiplied by a 2 by 1 matrix. These numbers are the same, so I can multiply them, and the result is a 2. So I should expecting a 2 by 1 answer. Okay, so what do I do here? I take 5/13 times 4. So 5/13 times 4 is going to be 20/13 plus 3/13 times 2. So that's going to be 6/13. And in the bottom I get negative 1/13 times 4. So that's negative 4/13 plus 2/13 times 2. So that's a positive 4/13. So on the top I'm left with 26/13, but that's the same thing as 2. In the bottom I get negative 4/13 plus 4/13 is just 0. And so we see, in fact, our xy, right, we're solving for, remember, x equals this A inverse B. So x equals this matrix here. So how does our answer for x compare to the solution above? We see, let me rewrite this. Where'd my cursor go? There we go. We have that xy equals 2, 0. So that's giving us the exact same solution we had before, x equals 2 and y equals 0. So it's just yet another way to solve. And of course, which method you happen to prefer is up to you, but it is yet another way of solving.